And gentlemen, so we are going to go ahead and get started by going over our two formatives from last week. So let me share my screen. Or sorry, not two formatives from last week. Our formative from last week, Friday, and then our formative from yesterday. So this first one, we are looking at photosynthesis versus cellular respiration. And so looking at photosynthesis first was what we were talking about first, and it's how the plants create their energy and oxygen, which they release to us, and then cellular respiration then uses that the glucose that we get, so in oxygen, to end up making energy and carbon dioxide, which we give back to the plants. And that's how our cycle works in terms of us and plants and why we exist together, why we would die without each other, which hopefully you probably learned a little bit about from biology. So if we look at this first one, the big thing to start with is looking at this lovely equation that we have here, which we have carbon dioxide and water plus some amount of energy. So we have this energy on our left, our reactant side, which makes our glucose, which is that C6H12O6, and our oxygen, which is the O2. We have to remember that when we have energy on our left side, that means that we are absorbing this energy. So that means the energy is being absorbed or that we have an endothermic reaction. When we look at our problem, we need to make sure that we're doing a few things with this graph to make sure we show our endothermic reaction, making sure our reactant side is smaller or lower on our graph than our product side. If it's endothermic, we're absorbing or gaining energy to get from reactants to products. So it should show an increase from reactants to products. If we're looking at our graphs, the big things I do want to make sure we remember is our axes. And that means that energy over here, our y-axis, should be energy and not carbon dioxide and or water. And then our x-axis down here should be time, or the amount of time or reaction process, how long it takes for this reaction to happen. So I saw a lot of people mixing up our axes here and putting other things other than energy and time. We got to remember that our energy is our y-axis because we're always having some amount of energy in this reaction, and time is just the amount of time it takes for those two to make our products. So that's why we use those as our axes. We're not going to put any of our reactants or products over there just because that doesn't give us enough information. The next thing I do want to talk about is a title for your graph. Always, 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 you need a title on your graphs. So if you miss your title, I am going to mark it wrong, which means you'll lose points for the easiest reason. So don't forget your titles. That is going to be important in any graph you ever draw, ever, especially in science class. The next thing is our wonderful reactants, making sure that those reactants are labeled on our reactant side, making sure we put our products on that products line, making sure that there is an activation energy. So that energy required to make this reaction happen. You guys did a great job with that. I just want to remind you that there is an amount of energy that's needed to get to the products. It doesn't happen just on its own. You have to apply the amount of energy needed for this delta H, plus a little bit more to make this reaction happen in an endothermic process. In our case for photosynthesis, it's because the sun's giving off light, and that light is a form of energy, and that's why photosynthesis happens in plants, is because plants absorb that sunlight. Making sure that your delta H here is positive, showing that it is an endothermic reaction where energy is being absorbed. Do you guys have any questions on this first one? I just went through a lot. All right. So then the second part of this question, so question, I think it was C, talked about cellular respiration. The first thing it asks you to do was to come up with the formula or the equation, the chemical equation for cellular respiration. It did tell you that it's going to be the opposite of photosynthesis. So what you should have noticed, or what you should have done, was replace our products in photosynthesis, turn into the reactants in our cellular respiration, and our reactants over here become our products in cellular respiration. So we should have flipped the two, coming up with our glucose and oxygen as reactants and our carbon dioxide, water, and energy as our products. When we do this, we should have seen our energy on our product side now, which means our energy gets released. And if our energy is released, that means our reactants over here have more energy than the products down here. If that happens, our delta H right here should be a negative value. So we got to make sure we have that negative in our delta H, showing that we've lost or released energy. Don't forget to always include that activation energy again, showing that there was a little bit of energy required to make this reaction happen. It doesn't happen spontaneously, but we have to put in effort for it to happen. That's where the activation energy comes in. Again, we do need our axes labeled, so we need to label our energy versus time graph. And we also have to put in a title up here, so energy versus time. Even I forgot to write it on this one. So don't forget your title as well. Any questions on 2B? All right, then the last part of 2 said, based on your graphs, which reaction will require additional activation energy? So both of them require activation energy, but which one's going to require more is going to be our photosynthesis, which was that graph 1. Because photosynthesis, if we remember, is an endothermic reaction, which means it has to absorb energy to get from our reactants to our products, but it also has activation energy it has to pass. So that means there's twice as much energy. There's the energy for delta H and the energy for for your activation energy. It has to go through all of this energy, not just the activation energy, to get to our products. So it's got to go through a lot more energy or absorb a lot of energy to make this reaction happen, versus this graph, our exothermic graph, only has to absorb a little bit of energy to make this reaction occur. Do we have any questions on 1 or 2? All right, then the last part was this wonderful graph here. As we're looking at it, we need to identify endo or exothermic. We need to identify the sign for our delta H. We needed to identify absorbing or releasing energy. So let's look at those first. If we look, our potential energy increases as we go from our reactants to our products. If that happens, we have an endothermic reaction, because our delta H is going to absorb energy, or it's going to be a positive delta H, as we have to absorb energy to get that reaction to turn into our products. As we can see, there is a lot of activation energy required, because it's got to go all the way up and pass our products and get to that activation point for our reaction to occur. So we got to apply or add a lot of energy to make this reaction happen. Do you have any questions on this graph? All right, so then we're going to go through formative number 2, the one we took yesterday. So if we take a look at this one, the first thing we should note is that this is a Haber process, which you don't have to remember, but it's just how we make ammonia, which is NH3. And so we combine our nitrogen and hydrogen to make this ammonia, and it does release energy. So that means it's exothermic altogether. That's not super, super important, but it is important to note that the energy is over here, making it our exothermic reaction. The first thing we're doing here is remembering that we need to show the absorption of energy, the releasing of energy, the forming of bonds, and the breaking of bonds in this process. So the first thing we need to do is to draw our molecular level or molecular view of these reactants and products, which means we have to draw our Lewis dot structures for each of our reactants and for each of our products. So if we look at nitrogen is N2. If we draw our nitrogen, we have 5 valence electrons on one nitrogen. And because it says 2 right here, that means we need 2 sets or 2 nitrogens in this compound. If we remember, all of our elements want to have 8 valence electrons to make a compound. Each one has 5. They have 2 that are already paired together, which leaves 3 unpaired valence electrons, which they're going to share so that each one has a total of 8 valence electrons, the 2 that they have on their own and the 6 that they're sharing. To show that we share them, we circle them together. So we're going to form 3 bonds between our nitrogen, or a triple bond that we're going to draw right here. Bringing back those 2 lone pairs on our nitrogen because those were not shared, but we need to show that each element has 8 valence electrons either on its own or shared. Hydrogen has H2, which means we need 2 hydrogens for this molecule. And we need to remember that hydrogen's special in the fact that it only needs 2 valence electrons in order to be stable, to be happy, which means they can share those 2 valence electrons that they have on their own. They can share these 2 to form that bond. So we're going to draw our hydrogen with 1 bond in between, showed by 1 line showing that they're sharing their 2 valence electrons. Now, if we look at that equation up above, we need to notice that there says that we need 3 sets of this hydrogen molecule, so 3 H2s, to make this reaction happen. So we need to draw 2 more sets of H2, or an H bonded to an H. Now that we have our molecules, the first thing we need to do is we need to have these molecules absorb energy. So we're going to bring in energy. I'm using a different color just so you can tell. You do not have to, but if you choose to, it does make it easier on you and me. So energy, you can label it energy or just draw the arrow, is going to come into each of these bonds. If we apply enough energy to these bonds are going to break. And I'm just going to draw squiggly lines showing that my bonds are breaking. So those bonds are going to break, and our ions or elements are just going to be flying around trying to bond with something so they can all be stable. Right now they're unhappy, they're unstable because we've broken those bonds. We've separated them, which means we want them to combine with something else. But now that there's hydrogens and nitrogens in the mix, those nitrogens don't want to be together anymore. They'd rather form bonds with our hydrogens. But if we remember, each nitrogen needs 3 bonds, which means each nitrogen is going to find 3 hydrogens to form bonds with. So those dotted lines are showing us that bonds are being formed. That nitrogen has all 3 of its bonds, which means the second nitrogen is going to take up the rest of our hydrogens. Showing that they're trying to form bonds with those 3 hydrogens. Now that we have that, we can actually draw those molecules, showing that nitrogen has formed 3 bonds with its hydrogens. But we have to remember that these lone pairs need to come back onto our nitrogen because those did not form any bonds ever. So that nitrogen needs to be there with its 2 lone pair. But if we look back at our first box, we can see that we had 2 sets of nitrogens forming 3 bonds with a hydrogen. So that means we need to draw a second one in our box. showing another set of NH3, which should match with our equation, which shows that we had 2 sets of NH3. Lastly, we need to show that energy is either absorbed or released. And since we absorb energy to break those bonds, when the bonds form again, we're going to release some energy. So energy is leaving, we can label that energy, and it's leaving our bonds, which means we can show our arrows leaving our NH bonds. And then if you really wanted to get particular about it, you would note that it's exothermic, and we can see that we broke 4 bonds and we made 6 bonds, which is why we have an exothermic reaction, because more bonds were formed than broken, and we know our energy amount there. Do you have any questions on this formative at all? All right. Then the last thing you guys are doing today is, oh, it's over here. You have a review for your summative tomorrow. On your review, it does go over endothermic and exothermic reactions, what they are, how to draw endo and exothermic reactions, making sure that you can identify them, making sure that you understand how to draw or understand the forming and breaking of bonds. And if you know all of this and you can do all the problems on this worksheet, you would be set for your summative tomorrow, making sure that you are turning in your summative. If you guys have questions about the review or about anything else, go ahead and stay. Otherwise, go ahead and work on your review. You do not have to stay to do so, but have a wonderful rest of your day.